All right. Good afternoon or morning, depending where you are. My name is Jim Eldridge, and I'm the Product Development Manager at Palmer Wahl. And we're going to discuss calibration of the DST600 Digi-Stem thermometer. We're also going to cover briefly a few other topics that pertain to calibration and the 21 CFR Part 113. So we're going to go through, we've got a short PowerPoint presentation here, and I'm going to try to read it from here. We'll go through, and again, first we're going to talk about 21 CFR Part 113 requirements. And I guess they can size these windows however you want on your computer screen. And we're going to go over calibration requirements that are in the standard and the records. Then we're going to review a sample calibration procedure and a form. And then we'll get to the actual demo that we'll be calibrating this unit here live. 21 CFR Part 113.40. You're all familiar with this. If you've been at FTPS seminars or meetings, you've gone over it several times, so I'll be brief in going through some of these slides. But the key I want to point out in this slide is that it is viable for the processor to calibrate their units, but if they do that, they must do it in accordance with the standard. And it states a couple things here. One, that the reference device you're using, which is your standard instrument when you're doing the calibration, that has to be traceable to NIST or another metrology institute, and that you need standard procedures for this. They also state that it has to be calibrated upon installation and at least once a year thereafter, or more frequently if necessary, to ensure accuracy during processing. And that step really is completely up to you as the user. If you're using a device and you see that it was to drift out, let's say you had a thermocouple device in there, which is why no one really recommends that, and it drifted over a 6-month period and was out of tolerance, then you would need to pull that device in and calibrate it more frequently. We recommend 1-year calibration on our RTD thermometer system. The standard goes on to state that a temperature indicating device shall be accurate to 1 degree F or ½ degree C. And the old standard, if you remember, just said that your MIG had to be accurate. And now they have put a number on here. The specification for our Digi-Stem system at the temperatures that most of you process at, up to 300 degrees F or below, is 0.3 degrees Fahrenheit. So it exceeds the specification of the standard, but the standard is 1 degree Fahrenheit. It goes on to state that records of the device or reference device maintained by the processor shall be established and maintained in accordance with 113.100. So what this is telling you is if you're going to do the calibrations in your own facility, you have to make sure that you keep the records, and they have to be in accordance with this paragraph here, okay? And we'll discuss that in a little more detail in the next slide, I believe. Now, it does, let me point out that where it says maintained by the processor, if you're using a reference device, like what I have here is a TM612, one of our meters, and a probe that I'm using as my reference device for the calibration we're going to do, you would most likely send that back to our lab to have calibrated. Well, we're going to do the certificates and the data in accordance with that standard. So you would be getting that from us, but you still need to make sure that you hang on to those certificates and keep them. The 113.100, this paragraph, and I won't go through everything, this is for the temperature indicating device, and it basically says you need a tag seal or other means of identity, and you can't see it, but on the top of ours we have a serial number tag, a calibration tag, things like that. There is a tag on our probe here, and that also has a calibration tag, which tells you the due dates of the calibration. I'm going to slide that down here so it doesn't fall in my hot water bath there. So you do have to, once you calibrate it, you need to label it. And certainly anytime you're calibrating a device, that device should already have a calibration label on it. It will say that it's due July 18th, 2014, for example. When we calibrate that today, you need to remove that old label and then put on the new label. You don't want multiple labels on your devices with conflicting dates. Name of manufacturer of the device, the identity of the reference device, so again that would be manufacturer, model number, and if it's calibrated externally, if an outside facility is used, then you would have a certificate of accuracy, certificate of calibration, or other document, and that needs to be traceable to the National Institute of Standards and Technology or other national lab if you're not in the U.S. Who calibrates it should be, you should always have whoever's calibrating these sign off, and then it's a good idea to have them reviewed by your quality department and their sign off also. The date and results and any adjustment that's done on that, and the date that it's due. This is basically the identical thing, only this is for the reference device. I really doubt that any of you will be calibrating your reference devices. That takes equipment and baths that are much more stable and accurate than what we're doing using to calibrate the TID. Calibration record document. The calibration test report is where everything's going to be recorded at, and that is for the specific calibration. And it's important that you file all those in a location where you can get to them also, because inspectors may want to view those. If you're doing this yourself, you will need the document itself, and you won't be able to see this, but we have examples of it here that I'll put up on the screen in a second. But there is a test data sheet, and then there also will be a procedure. And I believe we got those right, Megan, that we can look at. We'll look at those in a few slides. So you have to have those. That procedure can be in the whatever format your company's quality procedures are written in, really. This is a sample calibration document, and this is based on our documents that we use here. Of course, ours would have the letterhead up here and address, phone number, all that stuff. But this is the cover sheet. We typically do, when we do NIST certifications, it's at least a 2-page document. The first page is the actual certificate of conformance that is NIST traceable, and it's got all the customer information here. This will be the standards that it's calibrated to meet. We have an uncertainty statement on ours, and I don't think the 113-100 requires an uncertainty statement, but that's generally what's required by the other calibration standards, the metrology type standards. An attachment, and we just note that there is an attachment with this. Here's where we would list the procedure that was used. So that would, in our case, we use work instructions, so we might have QCW dash and then a number. Test report number, that's a unique number assigned to the document, and that number also gets printed on our calibration tags here that we put on. It'll say NIST number and then have a number. So if you were to lose a document and you give us that test report number, we can recall everything done about that and reproduce that. And then there's a signature block on it. The second sheet of that is where actually the data goes. And this particular one was laid out to where this is for a single calibration. So again, we have information on our unit up here that's being calibrated. We have data type here, as received and as left. So when we're calibrating, and we'll get into this in more detail, I'll review that, but basically, if we've not done any adjustment, some of these used to be called before adjustment and after adjustment, and it's important you know that information. We have our specifications here, and our data gets filled out in this field here. And then something else that's required is you have to know what your standard instrument was. In this case, we would be putting our TM612, the information about it, its serial number, model number, calibration date, calibration due date, the NIST number for it, and description, and then the probe also as part of that. And then down here's where the person's performing the test, and there's a QC acceptance here for a quality inspector to review all this for accuracy. 21 CFR, the marking requirements, it does state each temperature indicating device shall have a tag, seal, or other means of identity. At the factory here, we put the model number, serial number, the date of manufacturer on it. And then this is a sample of our calibration sticker. We use a Brother P-Touch label maker. They're relatively inexpensive labels. They come with software, and you can create just about any label you want. You're limited to the colors of materials, but we use a silver with black, and they're a very durable label. And then you can see we've got the date it was calibrated. Now this is an old one, obviously. Date it was calibrated, the technician that calibrated it, and the due date, which in this case it was a 1-year calibration interval. There's the NIST number, so we can trace all that information back from that number. And then one other thing we add, because this is a unit that came back to us, this is our order number. And in this case, this was a new unit, and the order number matches our serial number, you can see. But if you were to return that a year later, this number would have incremented by then, so it wouldn't match any longer at that point. But that is not part of the requirement to have that order number there. Okay, and now we're going to review a sample procedure, and Megan is going to share our desktop here so that we can view this. So basically what we have, and this is a calibration instruction similar to what we use. This is our format, our ISO 9001 documentation system, quality system we use. So we have a purpose, scope, responsibility, definitions here, any references that we use. Equipment needed, we do have listed here what we're going to use: oil bath, high temperature, stirred. Again, this is a sample, so these documents are available. I guess we have we emailed these, or we will email these to you, and you're welcome to. This is a Word document. You can mark it up however you want, and go there from there. But we have list here, the equipment we needed, standard instrument, and in this case we've referenced our 612 with a 205-12 probe. Lab stands, miscellaneous tools, ambient temperature and humidity instrument. You do want to record the temperature and humidity that you're at. If you're doing this in a lab, that's great. I would recommend trying to do this in a temperature controlled area if that's possible. If you're doing it on the factory floor and it's 95 degrees out there, that may affect your accuracy when due to ambient temperature. If it's calibrated at 95 degrees, then if you're using that thing and now in the wintertime it's at a much lower temperature, you will have more of an effect of ambient temperature on We have a warning on ours, and then basically we go through, and I'm not going to go through all this in detail. You will get this and can review it, but setup, we do allow a 15-minute stabilization a period. And the other thing is we want to make sure these probes are installed to about a 4-inch depth or more. Certainly if it's a longer probe, you can do more than that. But due to the temperature conductivity up the stem, when you start doing lower immersions, you may affect the accuracy of that calibration. And then this is the data collection here. It's just giving some instructions on that. Here we talk about before data, and then we're going to record all that data in the appropriate places, and we'll discuss that when we're actually doing the calibration. And then afterwards you look for a tolerance. Does it meet tolerance or not? And is it in or out of tolerance? With our unit, as I said, it's 0.3 of a degree is the allowable deviation. So even though you've used this a year, it should be within 0.3 of a degree. The after data, we usually tighten those specifications after adjustment because that's when we're first sending the instrument out to you. So we want to make sure that there is still room, some room, if that unit does have some change in it over that next year's period. And then the after data is really same type of thing. Only you would have done the adjustment, which is what we'll demonstrate in this thing. And then this traceability, we use a database, an access database that provides ours. This was done for a customer who wanted a simplified method, so they were just using year, month, day, and then an N for the sequential number to do. And all that's acceptable. You just should have a procedure somewhere that specifies what that's going to be. And that's the procedure. We'll go ahead, Megan. I think I can do this. The next section of that slideshow is to go over the test report. And again, we kind of went over this. This you might be able to see a little better. All the information, model number, serial number, manufacturer's instrument number. If you give your instruments instrument numbers, the data before and after. If I'm calibrating this unit and we just bring it in, we're going to take the before adjustment data. This is the ambient temperature and relative humidity. We would record that. And then here's our calibration data. We'd put what the source is. In this case, it's a hot water bath. I did not bring any of our high temperature oil baths in here, so I'm just using this portable hot water bath. But we have our source temperature, so this is the nominal. If we were processing and we used 230, 240, and 250 temperatures, we might want to test it at all three of those temperatures. Those would be our nominal. When we get to our unit, whatever the temperature is on the unit there, I can't read that one, 167.9, that's going to be what we record in our indicated space. And then the unit under test is where the display reading goes. Deviation is the difference between these two. This would be from our procedure, so if it's before data, it would be 0.3. If it was after, it'd be 0.2. Then we check if it's in or out of tolerance, or right in or out of tolerance, or however you choose to convey that information. Standard instrument description, that would go here. At a minimum, you would need a description of it. You should have some number assigned to that, although you could use model and serial numbers. Have the model number, serial number. Here's its calibration information, and here's the test report number. Okay, and then bottom is who conducted the test and QC acceptance. So this is a simplified one that was done in Excel, and we can go into the procedure now. So this is our DST Cal. Before we get to that, I'm going to step around here. And I can't tell if I'm in the image or not because I can't see it from here, but that's all right. Basically what we have is the Digi-Stem we're going to calibrate, and this one has a remote cable on it. This is our standard instrument. Again, that's a TM612, and It's got a 4-wire RTD probe up to here. I do have an ice bath sitting back here. We will be using that. When I turn that on, this motor's kind of noisy, and the slurring of the water and ice in there. So I'm not sure how that'll sound. You may need to adjust your volume. This is just a little heated circulator I have, a portable circulator, and it's limited. I'm in a plastic container, and we're 168 degrees, which is pretty close to the limit of this, but it is pretty well circulated, so we do okay with that for demonstration purposes. We do not use that when we're calibrating. And then I have my procedure that we would follow, though you may see me not really referencing it, just because I'm trying to get through this quickly so we can answer questions. And I have a calibration form. And again, we'll go through some of that. Now, as far as the Digi-Stem goes, if you're doing calibrations and you buy DST Cal, you only need that when if you're gonna make adjustments to the unit. To do calibrations and check the accuracy, you need a standard instrument and baths, and certainly water you can't use at processing temperatures. So we would use oil baths, and to do that, with an oil bath, a standard instrument like this, and a form, you can do your calibrations. If everything's in tolerance, you're good to go. If it's out of tolerance, or you want to try to get it a little closer or make adjustments, also our calibration does things like associates the probe, lets you change the refresh rate, things like that. So that's our option of DST Cal is what we call it. And what it comes with is the software, and there's a USB cable here that plugs directly into your computer. And then there's an interface box here which has the serial to USB converter in it. And then we have a short cable for going to the unit. And you can see over here that I do have that hooked up. I do want to stress a couple things. On that cable we have 3 white wires and a red wire, and I hope you can see this, I'm not sure. But the red wire indicates pin 1, okay? And then on the PC board, and this is just the PC board only, yours certainly will be mounted in the cover assembly there. We have 4 pins up here. This blue jumper is where you change it between degree F and degree C. And there's 4 pins to the right of that, and it's actually labeled calibration port, and it's J3. And the pin that's closest to the FC pin is pin 1, and it is indicated by, there's a small number 1 there and a number 4 on this end. So you want to make sure that red wire gets plugged in to that pin, and then that's the proper connection to that. Once you do that, then this unit will connect via this interface, and that's how we load data into here and do the calibration. Okay, now as far as DST Cal goes, I'll go over that here. We have the screen here. I've got this right, yeah, okay. So there's some controls up here, and most of those, like this has Fahrenheit or Celsius. That's not a concern for doing Digi-Stems. That is really meant with this software supports several different models of our products, and one of those does have a 4 to 20 milliamp transmitter on it, and that is for setting the transmitter characteristics, because those are done in degrees. Under the file, there's an activation, which when you first get it, there will be a number, I think, you type in that comes with the CD. I think it's printed on the CD, so you may have to copy that down. You enter that into the window. You can also check for updates or exit. So what we have here is the module configuration information, and it gives you the serial number. And right here I'm using DST Cal. Here you can see But it'll tell you the firmware revision in there. The serial number again repeated here. This is LCD refresh, so when we roll over that, it tells you the valid range is 0 to 40 periods of 250 milliseconds. So with a 4 there, that's 4 250 millisecond periods, or 1,000 milliseconds, which is 1 second. If we're going to change anything, and I don't have a keyboard, but Megan does, so you can put 8 in there. And I think we ship these set at 8, I believe now. But you notice she already hit enter. But once you populate that, the set button came up, or you can hit enter. So that's set now at 2 seconds. Low battery check. Again, this is 250 milliseconds, so this is like every 5 minutes. And you don't really need to mess with that. Over here's the calibration data on this unit. And there's 2 methods of calibration. There is one, I'm just going to jump here for a minute, the ohmmeter calibration. If you were a calibration lab, you might want to do that. We do that when we initially set the unit up. It takes some precision resistors to do that, so that's not necessarily something that you would typically be doing in a food processing or in any user's facility. But once that's done, that's what these numbers up here are calibration numbers for the electronics of this specific meter here. R0 is the resistance at 0 degrees Celsius, and when you buy a unit, our probes will be marked with a tag with R0. It also appears on the paperwork, I believe. And what we've done is to adjust out some of the error that's inherent in RTDs. We adjust R0 and set our meter for that. So that basically lets us offset the error that's due to the R0 component of the equation. And I'm not going to go into all that, and you're probably thankful for that. But that's what that does, and that's what we're going to be adjusting here. We'll talk more about that once we do the calibration. These units have a serial number in them, or probes. If you're using a cable under 30 meters, I think it is, then this is there's a serial number chip built into the probe, and that's what this number here is. That's a unique number. The company that makes the chips automatically programs that number in, and it can't be changed. So in this case, our probe and meter are tied together. If I was to hook another probe up to this meter, it would just give me an error on the screen over here. It would say PRB, which indicates to me that I've got the wrong probe hooked up. We can disable that, and that's a checkbox again. And what that does is that is for if you're running cables and we've had customers that have ordered 100 meters of cable, a couple 100 meters of cable. If you're anything over 30 meters, you will need to disable that, because the driver, that chip that's used in here, just can't drive that signal on that much wire. That length of wire, the resistance gets to it. So that's what the enable probe ID is. If we're going to change the probe, and again, this is where I am not prepared, my apologies. I would disconnect the probe, connect the new probe. When I did that, and providing this is enabled, my meter would say PRB on it, telling me I have the wrong probe enabled. I would come down and I'd hit this capture probe button. Once you do that, it'll go out, read the new probe, it'll tell you what it is, it'll ask you, do you want to associate the meter with the new probe, this number, and your answers are yes or no. If you say yes, that will now allow that meter to take data from that probe, and only that probe. A meter can only be associated with one probe. And then your display, instead of displaying PRB, will go back to the current reading. Change the probe and hit capture probe. These are the this is more for people doing electronic calibration. If you're doing that ohm meter calibration there, then the only option for the people using this program is to save these active defaults. And if for some reason they do something wrong, they can always restore to the factory settings. But all that is restoration is, that won't affect probe ID, that won't affect R0, and it won't affect these. It really is the calibration settings for the electronics of the instrument. Okay, so now we're going to go through this, and we're going to do before calibration, and I may be in and out of the picture here, I'm not sure. But I have my form here, I've got my procedure. We've basically got our bath and it's stabilized. Our meter is installed in the bath, and our standard instruments in the bath, or our meter's probe is, okay? And what I have, I would fill out all my paperwork on here so that I write manufacturer, Wahl, and I'm not going to go through this, model number, serial number, and I'm taking before data. Some forms it's possible to put before data here and after data here and do it all on one form, and that's really how most of ours are. It's just this sample wasn't. I would record the ambient temperature and the humidity from a standard instrument again, and I don't have one here. We have them in all our labs and production areas. And then that standard instrument technically is also part of your standard instrument description down here. So I'm ready to take data. I'm in a water bath, and my nominal temperature is 170 degrees Fahrenheit, and our actual temperature is 167.94. Our display reading is 167.4. Now our deviation from our procedure, we said it was 0.3 of 1 degree Fahrenheit. So my allowable deviation is 0.3 F, 0.2 F after. So my display deviation in this case is 0.54 degrees, so that would be out of tolerance. Now, this is not the norm for our units. I purposefully miscalibrated that unit prior to our show here so that we could go through the calibration. So we have a reason now. We're off by a ½ degree, and we want this thing a little tighter. So the procedure for doing that, I'm going to take my standard probe out of my hot bath, and you'll see our temperature dropping down on this thing. And basically I'm going to turn the ice bath on, and again it's kind of loud. I don't know if you'll hear me or not. I think so. But I will turn the ice bath on and let this guy stabilize, and that will take us a minute or two. You will notice, you may notice that said air, and if you use our units you'll see that. When we're going through an extremely rapid temperature change, I just plunged this into ice. We have air detection circuitry in there that checks the electronics, and the method it does that by is measuring the current through an ultra precise resistor, and then measuring some other ultra precise resistors that simulate temperatures at 180 and 250, I believe it is. And if it sees an error in that, it will display ERR on the screen. If it displays ERR and stays there permanently, there's a problem with the electronics. That doesn't happen very often. So I'm going to turn the ice bath on, and then once that's stabilized, we will do the calibration. Yeah, that's not too loud. I'm sure you can still hear me. And this is in this is a bath like we use in our production areas. If you've seen me do these demonstrations at other locations, I frequently use a insulated coffee mug with ice and water in it and stir it, and we get a close enough calibration for doing demos on. But there is, if you Google ice baths, NIST, National Institute of Standards and Technology, they have instructions on proper ice baths. This one's a stainless steel dewar, which are quite expensive. This circulating pump actually has a tube down in it where we draw water off the top, circulate it down in, and back up through the ice. You can also get good results with just packed ice and then fill all the air void with water. And of course it has to be crushed ice, finely crushed ice. And let that sit and stabilize, and that will get you also real close to zero. And I can't see, there it is. Okay, so our Digi-Stem's reading a little bit low, which we expect. And what I'm going to do, we've selected probe system calibration from our drop-down menu here, and we're going to hit calibrate button, and it's going to pop up a window here that will tell us to put the probe in an ice bath if we haven't already done that. We've actually already done that, and it's a good idea to let it stabilize. We're pretty close there. So I'm going to hit next. It runs through a 10-second stabilization period, and then you'll see a screen pop up with a bunch of numbers in it. So what it's doing, this here is telling you how many counts. We take 10 readings, and this is giving us a running average. Once we reach 10 here, this capture R0 button became active. It was grayed out prior to reaching 10. And now this actually helps us in looking, if we saw this average, running average of R0 continue to drop, we know we're not at stability yet. But since this guy is staying pretty stable, it's going up and down both, that we know that we have gotten that stable. So right now, our R0 over here is 99.980. And we're reading about 99.92, 918. So we're going to capture this R0 here, and it asks if I want to calibrate the module with this value. I'm going to say yeah, because that looks about like what I was seeing over here. And it says it's performed it. So we're going to say okay. And now this part takes a few seconds for it to do. And I'm going to turn this off while we're actually doing that. So now this guy, what it's doing is communicating over that serial link to this device. And now you can see that R0 has been populated with 99.9157. So what we just did was we used the DST600 meter as an ohm meter to measure the resistance of this probe in an ice bath at 0 degrees C. Okay, so another method is to use a precision ohm meter, and I think if you look in our operator's manual, we explain those things. So we've done that. I didn't notice we were reading about 32. I'm gonna put this guy back in here now. We'll get this warmed up, because now we've done the adjustment, and now we put that back in, and now we need to let this stabilize. Again, we want to make sure we have 4 inches of immersion on it. We want to make sure that we're close to our standard instrument, and when you're doing calibrations, make sure that both these probes are about the same depth. You don't want your standard instrument up here and the probe you're calibrating down here. And remember that the sensing element in these devices is about the bottom ½ inch is where that sensor is located. So that's really the critical part of that. So we now, let's see here, we're still coming up on that. So what we're going to do now, we've done our adjustment, and since my form has one before, I would put in my standard instrument stuff. It's a TM612, all that, and I'd sign off and date that 7/18/14, and that would be the first page. Now again, you could have another block underneath there, this same data for after data, and put it all on one form. But in the case of this one, I haven't done that. So what we're going to do now is I've got another copy of the same form, and I'm going to fill out all the information again, Wahl, model, DST600. Now this one is going to be after data. And again, we'd record our temperature, humidity. I'm in a water bath, and my nominal temperature is 170 degree F, and we're getting close to being stable there. And my allowable deviation is going to be before's 0.3, after's 0.2. Standard instruments, the same thing. It's TM612, some serial number, RTD meter and probe. Okay, so if we're going to take this now, my actual temperature is 167.94. So the indicated of the source is 167.94. And this particular meter, I think in Fahrenheit, it gives you 0.02 resolution. And our unit under test is 167.8. So if I put that there, 167.8. And you will see these guys fluctuating some, so you just kind of have to integrate that yourself or take multiple samples and then average those, or however you choose to do that. So in this example with those numbers, our deviation is 0.14. And that's pretty good for the setup that we have here. We typically get that or better. But now we are meeting our 0.2 degree after data, and the intolerance, it is intolerance. So we would check that off, complete it, sign it, date it. And remember in the standard, it said that you have to note the amount of adjustment. And on old, I guess, MIG thermometer reports and things like that, sometimes they were filled out and said this much adjustment was made. The way that's done with this is you've got a before data that says you had 0.54 degrees error, and you've got an after data that says you have 0.14 degrees error. So our adjustment was 0.4 degrees. Our calibration improved that by 0.4 degrees. Now, one of the reasons you want to use that data is that helps you determine if a unit is going to be is still functioning properly. If you see regularly where you have 0.8 of a degree error, then that needs to raise a flag. You know, you need to first make sure that your standard equipment's right and your setup's right, your baths are good, you're in the center of the baths where the temperature's controlled better, your fluid's good and viscous and all that. But if you continue seeing large amounts of adjustment you have to make to something, it's probably time to send that unit back to whoever manufactured it. So that, I think, completes the calibration. Again, we used that program there to do that adjustment, and then we sold the data, the after data came in. So I see a question from Kevin. Is plus or minus 0.2 pretty standard for after tolerance? Well, I used that on ours because our unit is spec'd at 0.3, and these things only have 1/10 of a degree resolution. Normally we have, for more precise instruments, an equation we use, but you wouldn't want to cut it down with this instrument. You wouldn't want to cut it in half or anything like that. There really isn't much drift. It's possible that you as the processor, remember the FDA allows 1 degree accuracy on this thing. So it's possible that you could say, well, we're okay with it being 0.3 before data and after data, or even 0.5, and that's up to your quality department and what your needs are to fit your processes. Hope that answers it.
Next one.
John, crushed ice bath can be used instead of a circulating ice bath. Yes. If you look at the NIST paperwork, if you take crushed ice, now they do specify it should be distilled water that the ice is made from, and distilled water that you fill it with. And the reason for that is that certainly if you're using soft water, there's a lot of salt, and I have no idea what soft water melting point is, freezing point is, but it's not 0 degrees C. But we honestly, we just use our tap water here. It's fairly clean. We do test these ice baths with an SPRT, and they're usually within 1/100th of a degree or so. 10-15 thousandths of a degree is what we get out of this particular one. And you certainly can get, you know, not quite that accurate in just a insulated vessel of some sort, but you'll get close to that, and it would be close enough for this, I think. Certainly, you can email us any questions or call us, and we'll be happy to talk to you personally. And Megan's putting my email address up there now. Hopefully, you can see that. And I'm at extension 330. Kevin Wilgus, have you ever heard of allowing up to 66% drift before making any adjustments? I don't think there's any, I'm not familiar with anything as far as standards go that specify that, but I would say that that's probably feasible. Again, if that fits in your requirements for accuracy. If your quality department has a mandate that they want the TIDs to be within 0.3 of a degree, and when you get it, it's 0.2 of a degree out already, let's just say it was 0.2, and you received it, well, at that point, you really can only give it another 50% of its error to drift. I guess it depends what you apply the percentage to. But really, as far as the FDA goes, you have to be within 1 degree. And then anything your company dictates that's tighter than that is what you need to meet. But those numbers are up to you to determine, and you would write them and put them, just document them in your test procedure. Well, if there aren't any other questions, again, thank you. We appreciate your business and hope you found this informative. Again, thank you. And if you have any questions, please feel free to call us.